All right. So we'll get started with today's class. I'll open the quiz. I think it's the quiz number 7. So the quiz is the number, I think is matching the lectures. But I'll make a note as I open the quiz 7 because I think that some folks are confused about that. So today, we're mostly done with D3. Today, the last thing we're going to look at is how do you use it for maps. Yeah, and then we'll work on Python notebooks visualization next week. All right. So I'll get started with the topic of today, that is basically 3D and how we understand 3D information, and then how do you build and design maps. All right. So the first part is heavy on concept about how the brain interprets 3D information. So that's all under the umbrella what's called depth perception. And we'll finish it up with some lesson learns to learn from that. And then the second part is a little bit more detailed because it introduces the maps, how you create maps. And that's important because, as we'll see, the math of creating the maps are important. Different projections are useful in different contexts, so you need to understand what a map projection is and which projection to use for which type of maps. And then we'll see how you build maps with D3 and Mapbox and others. All right, so when you think about visual information and how you understand it, from the perception point of view, then you have this picture here where we understand depths in terms of these 3 axes. This is egocentric, meaning that this is based on our everyday experience. The direction that is right in front of us is the one that encodes most of the time the depth information. But obviously, if you turn your head to the sides, then the same happens, and also up. Now, usually when you look up, you either have a roof and there is not much interesting to see, or the sky. So in that case, the 3D information is usually not relevant. So most of the time, towards away is the direction that we're considering. So when you look at a scene, how do you gather through your eyes and through your brain the information about the depths? So you have essentially 2 ways to do it, either with using both eyes, and in that case, it's what is called binocular vision, or using one eye. And depending on which way you go, the clues are different. For images, everything that is visual is important to us, but you have also, in the case of your life, information is coming from the fact that you're acting on the muscles that are in the eye, and the brain uses that information to understand how far things are. So the second category that I just described is what is called oculomotor, that is movement of the eye. induced by the muscles that control the eye. And I'm going to describe it briefly, but again, that source of information we only need in real life and or when we're looking at physical objects. Most of the time with visualization, you're staring at a screen. And what is important is the monocular information coming from one eye. That here is as these two subcategories that are static and motion-based. So those are cues that come from static images or from movement in the images, such as videos or animations as we've seen, right? The binocular part is also sometimes used. If you go to see a movie, that's typically what, in 3D, that's typically what is used, right? And there you use different techniques that are able to basically recreate the same type of input that that the brain is using in real life. So briefly, again, I color code the background of the slides for the things that are you don't need to know, but it's good to know. It's good to know the outside of the context of the quiz. So this one is the oculomotor, and the reason is that this is only useful for physical objects. And you have essentially these two mechanisms that we use in our brain to understand how far things are. The first one is accommodation. So this is what you do when you squint your eyes to try to focus on something that is close, for instance. And as you're doing that, what you're actually acting on are the muscles that control the lens of the eye. And you're basically deforming it. And that impacts how the rays are converging in the back of the eye in the retina. And so the brain uses that information that is coming from the muscles. It controls it. So this is again a process that goes both ways. And that is used to gauge the distance of the object. For binocular, you have also a similar clue. That is that when you're looking at some object in the distance, and then it's far away, the depth information is not really important. And you're looking with each eye very far. And so you can assume that your eyes are basically parallel one to another in terms of the direction of sight. But then as you focus on something that is closer, then you tend to do what is called convergence. That is that you move your eyes so that the direction of sight is for both eyes directed at the object. Again, what the brain does is that it commands that action. So this is a bottom-up approach, right? And then you have also the top-down, that is that the muscles send back a signal to the brain saying that this is our current setting, and the brain understands depths from that cue. All the rest of the slides here have to do with the thing that we're mostly interested in. That is, how do you understand depth information using visual cues from either static or animation cues that are in the picture. So the big category here is what is called the pictorial cues. So pictorial just means static images. And and that's what we're mostly interested in as long as we're thinking about traditional charts. So these are the list of things that you can do to create the impression of 3D with charts. And so we're going to go and look at each one of them in turn with a simple example, so you understand what they are and how they work, and if you may want to use them. So the first thing is and these are you can think of them a little bit as illusions, because what we're doing is that we're working in 2D and we're tricking the brain into making him believe that it's 3D information. But the process that is behind that obviously is the one that the brain is using with real 3D information that we've been developing over very long periods of time through evolution. So the first clue here is about occlusions. So whenever you see two objects here that you see these are completely 2D objects, right? If there is a gap between them, then you understand them as different objects. So we're going to see there is a connection with the theory that is the Gestalt theory of vision that relates to that. But for the moment, if you look here at the same picture with the same object, regardless if you have here a piece of A, what the brain is doing is that it's completing the figure and trying to understand the object as being in 3D space. So when we look at 2D images, and this is a thing that we're going to see over and over again, the brain thinks of the object as being 3D object, right? So if there is a gap between the objects, then we perceive them as separate objects that have whatever shape they have. But if there is no gap, then the brain is going to think that this is a 3D scene. And here it makes sense that we have a square that is on top of another one. Even though there is no light colored square, the brain is going to build it for you. And that's how you understand it. And so here, what is behind it is, I don't know where this is doing strange things. It is this interpretation of occlusions that are created in real 3D scenes by one object being in front of another one that is farther away. The second clue is what's called the linear perspective convergence. So this has been known for a number of years, and you see it here in a painting. So artists have used the fact that things that are farther away towards the horizon are seen as not moving when you try to change perspective, and that materialized by the fact that they basically are on a line that is somewhere here in the middle of the picture, where all the rays converge. And if you move about the scene left or right, then the objects that are in the forefront are going to have more movement. And the way this is geometrically described is by these lines that basically converge to this line that is towards the middle of the picture here, that is at the infinity, if you want to think of it in those terms. Those lines, you can use them to basically design your painting. And here you can see that all the geometry of the buildings are based on these lines that converge towards the infinity. Relative size, familiar size has to do with the fact that we have learned the size of certain objects. And so both the knowledge of what the object is and what is normal size is used by the brain. And the fact that whenever the object is seen is going to create a project in the retina that is proportional to what its distance is. Inversely proportional, sorry. So the farther the object is, the smaller the projection, the closer it is, the bigger the projection. And the brain uses both clues about the knowledge about the object and the size of the projection in the retina to try to understand the distance. So this you can use, for instance, in this simple example here, where these are all trees. So you know that the trees that are going to be farther away on a line here that is materialized by the horizon are going to be closer to the line than those that are close to you. So the more they get to the line, the less the vertical displacement you're going to see, right? And so here what we get is an illusion of distance with exactly the same three objects in one line, just because the brain is used to understand that the farther away the objects, the closer to the horizon, the line on the horizon they are, and the less their displacement is used to take where the line is when you move them farther away. The way things are seen in terms of texture is also another clue. So here you see what is the illusion of 3D. Who knows what is happening? That is just created by the fact that the texture is set up so that we're going to have seizures here if it doesn't stop. What do you think we do? Okay. Yeah, on the screens, I think it's fine, no? Oh, it's the same thing? Oh. So maybe it's the Zoom that is making trouble. All right, I don't know. Okay, anyhow. So, fingers crossed. Let's see what happens. So here the illusion is created by the fact that the circles are, you see, slanted, and they're closer together on the sides of this wave, where it's corresponding to the back side of the wave. And that is basically what happens in real life. If you're looking at sand dunes, for instance, then the objects that are at an angle are going to be foreshortened. And those that are in front of you are going to have a projection that is closer to the actual object that you're trying to see. So here we're looking at the circle. So here the circle is closer to a real circle as opposed to an ellipsis. And so the combination of this foreshortening and also the change in size, because you see that the closer the dots are here, the bigger they are. gives you that illusion. The shadows obviously is something that we're using also to understand 3D information. And this one again, you can think of it as kind of illusion, but that's something that you can use in a chart to give the 3D perspective to the objects. So here, obviously there is no depth here. Yeah, there is no depth. There is just a blurred background that is supposed to materialize the shape, and the brain is using that in conjunction with the distance between the white square and its shadow to understand how far the white square is from the plane. The checkerboard plane, obviously, is the reference, and the brain knows that if you have a source of light, the closer an object is going to be to the plane, the smaller is going to be the shaded area behind it, and conversely, the farther it is from the plane and closer to your eye, the bigger the shadow is going to appear. Okay, so here there is just an illusion, obviously, that is created by setting up the shaded area with some formula that you can relate to the depth. So the shading is also useful for looking at 3D objects. And here you see another example. So this is a crater. And here what is unclear if it's a crater or if it's actually a dome, right? And your brain is going to make one or another of the inferences based on where it thinks that the light source is situated. Yeah. Yeah, we're going to see that. Yeah, but I think we discussed that already last week. That in the achromatic channel, if you remove, the achromatic channel, you can use the shading, but if you use the shading on colors on the chromatic channel, then you're basically removing the 3D effect. Defocus blur is what happens when you, with Apple has this new phones with the cinematic mode, right? So when you use a lens that is set up with a focal length that makes that things that are at a certain distance are focused only, then everything else farther away from the subject and in front of the subject is going to appear as blurred. So here in the picture, you see that not that focus, but there is trying to focus on the flowers, and so the background is completely defocused, and there we get this impression of 3D because of the blur that is between the forefront and the background of the scene. So these types of effects have been also used in paintings. So we mentioned that there is the foreshortening effect that happens, but also artists have used the fact that the farther away things are, the less precise we are able to understand them. So the objects are not as sharp, obviously. The colors, they tend to be less saturated. just because there is other light, that more light that is coming into play. And so the colors are not as saturated as you would expect. And usually, if you have a nice blue sky, then the color of the sky is going to impact the color of the scenery. And so you see this painting, for instance, the mountains are painted in this bluish color. And that is, again, all of these are clues that the brain is using to understand 3D. So all of those, they have to do with static images. Now we're going to look at those that are motion-based. So if you like to play games, then you're probably familiar with this one. So this is sometimes called kind of 2.5, 2.5D design, where you have different layers, and one of the layers is moving faster than the others, based on how close it is from the viewer. And then you get this parallax effect that creates the 3D, the impression of a 3D scene. So things that are very far, again, they don't move at all. So that's consistent with what we've said earlier. So again, the brain thinks about 3D all the time when it sees things that are coming together and or moving. So in this case, obviously there is no such a thing as one square that is in front of the other, but that's the impression that you get just because of the movement. Those phases are commonly referred to as deletion and accretion. Deletion when the object that you perceive as moving in the background is being occluded, and accretion when it reappears. So these clues, there are a couple of them here, and we're moving to things that are familiar to folks who work with computer vision. So here what we're doing is basically getting clues from the motion that have to do about the structure of the object. And again, it's the same principle as usual. Here, the dots that are farther away are going to move less than the dots that are closer. Here, they're randomly removing the dots so that you don't get a clue from the shape of the object. So you see that the dots are just flickering. They're actually not flickering, but they're changing as the object moves, so that the shape of the object doesn't interfere with your perception of depth. And here, the only clue that we're really using is the fact that we see the depths for these points from different points of view. We should see these points at different locations. So those that are closer to you are going to be seen with a larger movement. We could look at between here the extreme location where the object is like oriented to the left, and the time when it's oriented to the right. You see that the points that are in the background, it looks like a motion curve. The points here that are corresponding to the top of the Gaussian are moving almost two-thirds of the picture, whereas those that are in the background are really moving very right. And those are the clues that we're using. Again, so this is not stereoscopy, but you can look at it with just one eye, and the effect is going to be there, right? But it's similar to the same information that we're using when we have two eyes. And there what happens is that the closer the object, you see, the farther is the distance between the projection between the two eyes. So here, for example, the green dot is going to project all the way up here. And so if I look at where the same object projects on the right eye compared with the other points, you see that the other points are closer in terms of distance. So this distance you can encode it, and that's what people that do computer vision do. You can encode it in images, and you end up having what is called the disparity map, that is basically a discretized depth image, where here the lighter colors correspond to the closest objects, and the darker the color, the farther away. Yeah, I wanted to put a little note here. So this is not just happening in the eye. It's really the brain that is integrating, obviously, both cues. And people have found that there are actually cells that respond to this disparity. So there are cells that integrate the information and cells that detect the distance in terms of the retinal projection that then the brain uses to encode distance. So I'll show you a couple of more pictures that are illusions of 3D. For things that may happen at times as illusions in graphics if you're not careful. So here, this is a classic one that is called the Ponzo illusion, and that has to do with what we call size constancy. So this is the analog of the color constancy that we've seen last week. So here, these two white bars are exactly the same length, but because the background you see is from a real scene, we're looking at those with the understanding of the 3D information that is in the scene. And here you see the converging line for the perspective line. And this information makes that the line that is closer to the horizon is seen longer than the one that is close to you. Because if it's farther away, it must be bigger, right? Because it takes more space. So it's a conjunction of familiar shape, because you know what you expect that this rectangle is the same as the other one, and the 3D information that is here in the scene that creates the illusion. The Poggendorf illusion is another one that you may create if you are using the wrong colors here, as you can see. And in a bar chart, for instance. So here what the brain is doing is, because these objects are touching, so it's going to interpret it as 3D objects. And he has to make the decision whether this line is coming from the blue line, the black line is coming from the blue line, or from the red line. Because the colors are closer between black and blue, is going to associate it with the blue line. So your impression is that you see the continuous line, and you see that it's actually attached to the red line. So this one is rare, but you might do grid lines, and you make them slanted. That's usually not a good idea, especially if you use colors. Muller-Lyer illusion. This one doesn't, I think, often unless you start using arrows, which is always something that you can do. So again, the object is seen with in 3D, and here basically the fact that the arrows here are closed and here they're open tricks the brain into believing that this is farther, and therefore this needs to be more longer than this. So the line segment here is exactly the same as one here, but this one is perceived as being longer than this one because the brain thinks that this is something that is farther away. Necker cube. So this one I have actually concrete example in charts. So you're familiar with this one, and here it's what is called bistable, meaning that you don't know which face of the cube is in front, right? Because you can interpret it both ways. And so, yeah, I'll give you an example on that. This is another famous one that is called the Shepard turning table illusion. And I played around and open it and play with it. But basically what is happening is that this surface is exactly the same as one. And I know it's unbelievable, but that's the case. And the reason is that if you see these two rectangles here, they're not rectangles, parallelepiped. Without the legs here, you would just interpret them as two areas, okay? But because you with added here legs, then you think that this is a table, and the brain is thinking of it as tables, yeah. Because it's thinking of it as table, it tries to place them in 3D. This rotated version of the same thing is going to appear as different surface as the one that is there. If you want, I can maybe, yeah, if we have time, I can give you the tour, but yeah, you can go and play around with it, and you'll see that in Inkscape you can rotate the things, and you'll see that it's exactly the same. Here we have what is called the Ames room, and it's a room that is crafted to give you the illusion that here the familiar size conflicts with what is the geometry of the room. So you know what is the size of people. So you don't expect, you expect that the bigger they are, the closer they are from you. But the room is set up so that you have the impression that they are at the same distance, which is shocking here because we have one person that is half the size of the other one. Obviously, the way it works is that everything is distorted. So this person is actually closer to you, and this one is farther away. But the lines here that you interpret as converging are not actually using that geometry, and they're distorted. I think that, yeah, I didn't put a picture, but yeah. So the geometry of the room is basically this way. So here we have the person that is standing on the right side, and here we have the person that's standing on the left side, and yeah, the ground lines are something like this. Okay? And the camera is set up here. All right. Design considerations. So with all of this in mind, these are some examples. Again, there is a little bit of illusion in there that is happening, but what you want is to understand when 3D is useful and when it's counterproductive to use it. So in this one, there are several things that are done incorrectly. Can you see them? I don't know if I put the answer. Yeah, I put the answer in here. So the first thing is that obviously it's the pattern that so here they tried to do some bar charts, and they ended up doing this pyramid. So we're used to the bar charts, and we can tell the lengths pretty well. But here, when we use the pyramids, it's kind of harder to resolve the top of the pyramid. And with the data that they have, it's even more confusing. So you see that they seem to be grouped about at the same height. So we might think that the height is the same across, and that there are a couple of variations in size. So not using the bars, I think it's a problem. And the reason I think they did that is because they thought that with using this shape, you would have less occlusions than if you use a cube like this, right? Because then you would have quite a bit of occlusions. So here they tried to do the depths here as small as possible, and then they cut out something like this, right? And the result is not brilliant because it's very difficult to compare the height of these bars in 3D based on the shape that they have, right? On top of that, they put this texture. So we saw that the texture is a clue that the brain uses. But here you see that the texture is all the same. So it's inconsistent with the 3D. There is no foreshortening, right? The pattern is the same. The lines here are unspaced here and there. So they're sending mixed signals to the brain. You see that some of these things here, they're like they turn into these black rectangles that I don't understand what they are, but maybe. And then we have this grid that is in the background that is creating a nacre illusion, which is bistable, meaning that you can see it in two ways, and that makes your brain work harder and not seeing the data. Yeah. So these are from a blog that Tufti has on visualization, and they're very old, but I think it's from the NIH. And so they had this cancer charts. You can go and read in the blog, but you see they have the same type of bars here. We're not doing this anymore. Obviously, the use of the colors in these is very questionable. So you remember that you don't want to use darker colors for the background. So here they're using this dark green that is really interfering with the rest. Here is so bad that we cannot see the grid line. And then they used all this 3D. And you see that there is not much of a reason to use 3D. I think it's just again, we have the maker problem here, illusion. You better just do a couple of charts if you really need to have I mean, these are curves, so you can just do a 2D chart, right? So here they use the 3D, but you really need to use the 3D because it's a surface. The curves are on a surface, and the shape of the surface is important. Then you rather do a projection, and you have two 2D charts with a projection. It's going to be better for people to understand what is going on, because here with the occlusions, it's very very bad. Yeah. Yeah. So again, here it's both colors and the 3D that is not useful. So the main thing with the 3D in terms of using it in charts is the occlusions. So there are two ways to deal with it. So this is one of them. That is to simplify the projection. And the second way is to simplify the way you can actually move around to avoid the occlusion. So the 2.5D design is usually a good thing to do, but it depends on your data. So in this particular case, you see that they've color coded also the data based on the height to alleviate a little bit the occlusion problem. And their data is you know, in terms of occlusions, it doesn't seem to be impacting really the understanding of the data in this particular case. And for the angle that they've chosen here, right? So you have different things that you need to be mindful is when you're working with 3D, you need to understand what the projection is, how much is occluded, what would be a better projection, so to minimize the occlusions, and or other encodings, so that you don't rely just on the 3D information to show the data. The second problem is kind of more generic, and that has to do with the fact that when you're looking at data in 3D on a computer or tablet, it's complicated to move around. So the navigation is usually difficult for people to do. And you know, in games, usually what happens is that you're usually constrained to a plane, and so the movement is also egocentric. So you're basically trying to move as you would move in a real world, and that simplifies things. But when you have some type of surface that has here bars or something else that you're trying to use to visualize data, and you want to move around, then you're basically flying around, and flying is complicated. Okay, so people have invented all sorts of mechanisms to try to simplify things, and the maps is a good example. So Google has this Google Earth that it doesn't seem that people are using anymore. And the problem with Google Earth was the navigation. So today the maps that we're going to see, they're actually 3D. In most maps you can zoom in, and then you get a perspective view that is more of this simplified 2.5D with a constrained navigation. So depending on the height at which you're moving, and you're keeping the angle at which you are with the surface. so that you don't need to think too much about the movement, okay? And that works up until the point that you know the data are good for that, meaning that they don't create too many occlusions. All right. So this was the first part. So we understand a little bit how the brain works. And now I'm going to move to the maps. So I'll go at least 10 minutes and then we'll do a break and we'll resume. Okay, so maps have been around for quite some time. So here you see one example from John Snow. This is the original one that he created for trying to understand where the cholera epidemic initiated in London in 1854. So I think the epidemic was in the same year. And cholera is you can contract it through sources of water that are polluted. And so they were trying to find out where those cholera cases were happening. And eventually used the map to relate the cholera case to the, where people went to get water. And I think this is one of the locations here. This is a pump. You might have seen something that is for the same map similar to this. That is today called the dot map. So where each instance here is one of the persons who passed away from the disease. And you see that here the pumps are more clear marked. So these maps have been created with a purpose, and there is a team behind it. So they're part of what are called thematic maps. So there are a few examples of those that we're going to look at. For the dot map, you can obviously use it to associate one dot with one instance or multiple instances. So this could be a household with multiple people or just one person, right? So the thematic maps that the maps that we call thematic these days are formed in this 4 or 5 categories here. So we discussed the dot map. So here you see an example of a dot map with a color encoding that is either based on value or that can be the count that is associated with each one of the dots. The second example I'll give you a little bit more detail on it is a cartogram. Here what you're doing is you're coloring areas, but you're also encoding the data in distortion that is associated with each one of the areas. The choropleth map is what you're familiar with the election map, where you have a map that is colored per area based on some value that's related to the data. You can do the same thing with symbols, and usually you put the symbol in the center of the area where the symbol is should be located, if it's say for a state, or the location where the data is originating. And you size there the symbol based on the value of the data. So this is the same thing as you've done with charts, but here is not the support is not a Cartesian coordinate system, but it's the map itself, right? And then you have these maps that you use for weather and for understanding terrain. So those are contours. that relate to data that is 2D, or at least projected in a 2D plane. They could be, if it's atmospheric, right? Data, then it's actually 3D data that is projected on the map. And those are called isoplex or isarithmic maps. The term means really contours. So here is an example of the United States as a cartogram, where here the states have been sized to the data. And you see that it's not just the size is not randomly set up, but it's really acting on the whole projection because the state is still touching, right? So it's a overall deformation that is applied. So that the area of each one of the parts in the choroplast that we have here is deformed based on the data. So you'll see a few common types of choroplast maps that people use. So this one is called daisy mapping. So what happens with when you do a choroplast is that the resolution at which you have your data may not be what you want for the application. And so because it's the data are usually referring to a actual physical category. If you have some information about the area, then you can refine your estimate in terms of spatial extent of the data and end up with a better resolution map or a place map that you would have just with using, say, some subdivision that is related to the data that you have in input. So here is typically what is happening. So you have some population density data that here are by tract data. And so you see that the counts here are just corresponding to the tract areas. But obviously people live in cities, they don't live in the woods or on lakes. So what you can do is that you can refine this taking into consideration information about how the land is used. So if it's a wood, then you don't expect that there are people there, but for everything that is constructed, where you have cities and villages, then the density is going to be higher on those areas, right? So obviously you need to do some math to get to this point, and that's the process of what's called daisy mapping, which ultimately allows you to have this asymmetric map on the right that is more refined based on the land cover information. Okay, so that was for the types of maps. So now we're going to see how they're built, and then we're going to look at how to which projections are used and what to use for different types of maps. So I'll do a quick break before I go on with that. Okay. Yes.
Lab
Okay.
8, and then I finished it, but
It's not what it should be.
it's a little confusing. It's about why it's not just show the whole graph. I think it's just the column.
So the problem is that your SVG doesn't seem to start where it should. So you probably use the view box.
Mm-hmm.
Yeah, so don't use the view box. Just do a regular SVG with
Okay.
width and height, and then you set up the width and the height as you know how to do, right? And then it will fit what as you expect. Because they're using the view box because they're setting this up in the notebook,
Okay.
and so they want to do it a little bit different.
So it means that's
Now, what we need to do is tell the senior circles are pulled both together. Actually, there's something. That's what the only thing in the back now is that it's a low power. So if you want to know more about this, so here it's just setting up with okay. Now instead of part one, I there. Yeah, so here it can just size it to say, let's start with the yeah. So it's already deducted. Yeah, exactly.
All right. Okay. Okay, our maps are built. So the work with the map that people do is that they take areas that are you define on Earth and project them on a map that is in your paper, that is much smaller, and that is 2D. So these are mostly surfaces, but oftentimes you're also interested in elevation. So it's really 3D information. So the way you do it is in 2 steps. The first step is to basically understand how you model Earth. And once you have this simplified model that we're going to see is good for certain areas, depending on which model you use. Then you do the second step here, that is to basically scale and project in 2D. Okay, so for the first step where we're trying basically to model Earth, what people use generally is this geodesic system that is a simplified version of Earth. And you represent it basically as an ellipsoid with the major and the minor axis that is here. And you have obviously different ellipsoids that people have come up with. The one that is most used, that is used in particular for the GPS system, is this 1984 GPS 84. And these numbers are great. Okay. So all it's basically doing is modeling Earth as an ellipsoid that is centered on the center of mass of the planet. And these axes are defined based on some meridian here that is documented. So once you have this, then you need to understand where you are located in this ellipsoid. So we do this with what are called latitude and longitude. So those are polar coordinates that you're familiar with. And some parameter to encode elevation. So you can see the longitude and latitude, they're encoded at eastern and northing locally. And there is usually a different coordinate system that is associated to that. The latitude and longitude, when you talk about them, they're with respect to the ellipsoid. is the caveat that you can define the latitude based on the center of the ellipsoid or the tangential plane to the location where you're at. Most of the time, what you'll be using is the geographic that has to do with the normal to the tangential plane. And so that's how we define the latitude. And that's, yeah, most of what you'll see is using that one. Now, in order to define elevation, it's a little bit more complicated than that, because there is no such a thing as a mean elevation. And people use different references. So you can either base it on the ellipsoid. In that case, the altitude is based on the surface of the ellipsoid, and it's called geodetic. You can base it on the average sea level, and it's going to be called tidal, or gravimetric, meaning that is based on the gravity field on Earth. The way you compute this in practice is that you think of the planet of being made of water with the gravity that is coming from the land masses that is going to pull the water up or down depending on the local situation. And then you end up with this surface that is called a geoid that simulates, that tells you basically how the surface is deformed based on the gravity. And that gives you the gravimetric altitude reference. So this is what is encapsulated into what people call the vertical data that allows you to measure altitude. And obviously you put it together with the latitude and longitude as we've seen earlier. That define the horizontal data. And both of these things together, you people call that the geodetic data. Okay, so it's basic geodetic is just a reference to the fact that you're encoding both horizontal data with latitude and longitude and vertical data with one of these approaches. In practice, what it means is that when you have XYZ information, it will come in one of these forms, and people will need to tell you what they're using in terms of their reference, so that you can actually understand what the data relates to. So this is just a picture of the geoid, so you see that what to expect. Counterintuitively, the gravity is not directly, you can see, related to the land masses, because it's probably related to the height of the seabed that is playing here a factor and creating more density, and obviously the structure of the crust of the Earth. So yeah, so the area here around the Northern Europe is at higher level in terms of the gravimetry than the area here in the ocean. That there is, yeah, that looks more normal. Now this data, so horizontal and vertical, you can define them in different ways. You can have some that are based on geocentric, which means that they're related to the center of mass of Earth, and they work well in general for the planet, but they're not necessarily good locally. So if you want to be accurate locally, then what you do is that you move your reference point of to somewhere else, so that you can approximate better the surface of the Earth locally. And in that case, you talk about a local datum, okay? Where datum is, again, a geodetic datum, both horizontal and vertical. So the local datums, they're good for if you have local application, meaning application for the United States or for Europe, and the geocentric, they're good enough everywhere, but they're not great all over the place. How maps are built. So this is the second part. So now we are able to understand our point on the surface of Earth is going to project both on a horizontal datum and a vertical datum. And now we're going to see how to take this information and put it on the map. So this is done obviously with a scaling, but obviously we need to do something a little bit more because we're on an ellipsoid and we need to project this ellipsoid on a 2D surface. So something has to give. So here you see an example of a projection. And this little circles there, they're there to indicate what are the deformations that the projection is creating. And you see that the circles here towards the poles are larger than the equator. And this means that the areas are represented on the map by a larger surface than what they are at the equator. At the equator, yes. And the reason for this is that you take your ellipsoid and you need to unwrap it and put it on a 2D surface. That process is the projection. And by doing that, you create some distortions. So here you see that the distortion, the whole circle, so there are no distortions, but the distortion are the same in the two axes. And the only distortion that is introduced is the distortion of size. Obviously, if you get to the North Pole, then this is becoming undefined. So here your circle is going to probably become much bigger than what is shown in the picture. So the projections that you can use to accomplish this are going to work in such a way that there need to make some type of compromise between the distortions that are going to be applied to the surfaces, to the areas, sorry. And you necessarily will need to have one of these categories in that all are associated with one particular distortion. So instead of looking at the distortion, because that's not really what people are interested in, you look at what is preserved. So if you're interested in preserving the shape of things, then you'll use a particular projection. if you're interested in preserving the areas so that the areas are comparable, then you use a different projection. And obviously, each projection is going to be useful for preserving one property. And each map that you create, you will want to make it so that the property that is preserved is going to be useful for showing the information that you want to put in the map, right? So the different properties are listed here. I'm going to go through each one of them so we understand them. So conformal, as the name says it, is just about the shape, the form. And so here what we're doing is that we can recognize objects as we would see them if we fly above them in the map. So we preserve basically the shape of those objects. So usually those are contours. So the state contours or the countries, boundaries, all of those would be preserved. Now you see that the description talks about the shape of small regions. And the reason is that obviously you can only do that locally, right? Because again, we're looking at an ellipsoid. So if we need to put it in 2D, we can try to preserve how things look like in terms of shape locally. But if we look at the map of the world, we need to distort things as we move around, right? And this is basically what this map is doing, right? So locally here, everything seems accurate. But if I go farther north or farther south here to the poles, you see that these land areas are much bigger than what they are in reality, right? But the contours here locally are accurate. If I look in this area, I can actually understand the geography as I would if I would fly over those areas, right? And this is materialized here with the circle, right? So there is distortion that is a scale factor, basically, that is independent of the direction. And that allows basically to encode the shape of the small regions consistently. The equal area, as the name also says it, is going to preserve the areas proportional to what you would see if you would look at it from a plane. Equidistant, any distance between 2 points or along one or more lines are going to be preserved. So again, it's proportional to what you would observe in reality. Yeah. And then azimuthal has to do with the angle. So there we're preserving the angle. So we're going to see what this means, that those are usually useful for navigation maps. So the question is can you have multiple of these properties preserved together? The answer is no. You can only have one. And the reason is that, again, you need to unfold this 2D surface and put it in a plane. And so something has to give. So here, what we have decided to do is to preserve the shape of the smaller regions. So these circles, they look like circles all over the place, right? But then we need to cut the orange peel to allow this so that we can put it in the 2D plane. Right? So we cannot do both conformal and equal areas. It's not possible. So how people name those projections? They use basically the name of the person who usually invented it, and they refer to the properties that are preserved, and also to the surface that is used to do the projection. So if you use a cylinder to do the projection, so as shown here in the figure, then it's going to be called a cylindrical projection. If you use a cone, it's a conical projection. And if you use a plane, it's an azimuthal projection. All right? You have subtitled these because the cone, the cylinder, and the plane, you can move it across the surface that you want to project. So if it cuts it, it's called tangent or secant. And also you can orient it in different ways. So here you see, for instance, for the triangle, you can do the normal, the transverse, or the oblique. Okay? And obviously the projection is going to look different depending on what you do. So you with this in mind, you don't need to know the math, but what you need to know is what are some of the maps and understand how they're named that are most useful. So I'm going to show you those. So starting with this one, that is the Lambert. So that's the person who invented this map, this projection, sorry. Azimuthal means that it's using a plane, and equal area means that it preserves the areas. Right? So this one is, you can see it's, here we see an example where it's used, I think the USGS that is using it for the United States. And because it preserves the areas, that's useful for choropleth maps. One that is most used for choropleth is this one? Yeah, I think it's one. Is the Albers conic. So this is a conic projection. Albers is the inventor, and this one also is equal area. Now you see that this one is a little bit more complicated than the previous one. This is because oftentimes you want to show in the same graphic different land masses. So here the continental US and here Alaska, and then we get here Hawaii that is on there, and I think this is Puerto Rico. So in order to do this, you need to actually have multiple projections in each one for each one of the areas. So this is what is called a composite projection that is using 3 different parameterized version of this Albers conic. This is usually available. We're going to see with different. You can get it as one projection that you can just use as is. These are less useful, but they're used on other contexts. The Lambert conformal conic. The Lambert again is the inventor. The conformal means the shapes are preserved, and conic is using a conic projection. So this one is useful because the shape is preserved locally, and that's most useful for people who fly because they can recognize the areas that they're flying above on the map because the shape is preserved. Okay, so they don't care about the area, but they care about the shape of the coastline and you can recognize it based on the fact that it's conformal. The last one, the Mercator, and I think that this one is kind of the most important. So the Mercator is the person who put it together. Yeah, but you need to know that it's cylindrical and conformal. So again, it's good for the fact that you can recognize the areas, but you're distorting sides, right? And so here you see that again, the land masses are not at scale with one to the other. So for local application, this is good. And that's why this is the standard for the web, because when you're looking at your country, you have a map that you can use to move around. So all the maps that you're familiar with, Google Maps, the Apple Maps, and so on, they're using this projection with different variants, because they change a little bit the parameter. So the variants include the Web Mercator, I think it's the W3 standard, and you have the Google Web Mercator that they did their own. There is one that is called Spherical Mercator, and there is one that is based on the WGS84 that has the WGS84 acronym in the name. Okay, so most of the time you don't need to worry about it because you're going to use the front end, and the map has already built in the projection. But obviously, you need to make sure that you're passing the data in the format, latitude, longitude that is expected. This one is, sorry, I thought it was the last, or the second last. This is another type of projection that is useful if you're working with very local data, where precision is important. So here is an example with LiDAR data that are reconstructed for, I think this is the rate. The accuracy is typically half a meter or less. And you want to be, very precisely where each one of these LiDAR points is with respect to the planet. And so you use a projection that is good for that very locally. The military is also using this. If you own a property, then most likely it's the terrain is encoded in this particular projection. So in order to be precise, what you need to do is be able to define your projection very locally, and that's basically what they're doing here. And then you want also you're thinking about what is the square footage of your property, you need to be able to measure this on the map, right? If you have latitude and longitude coordinates, it's very complicated to do the math and do those measurements. So for this particular projection, what you do is that you have basically a Cartesian plane with north and east as your main axis, and everything is metric, so you can just directly measure distances on the map, and they're going to be very accurate. So the drawback is that you need to define it very locally. So this is done by bands, as you can see here. And each band has its own projection, right? And when you get the data, they are in meters with respect to the information of the bands. So here is this one is 48 north, which corresponds to the band number 48 on the northern hemisphere. And for that band, these are the coordinates of the point. Okay. So the way you tell them apart from the other data is that these are in meters and the others are angles, right? That are latitude and longitude. So the name of this one is the UTM. People know them mostly by the acronym, and it's called the Universal Transverse Mercator. Universal meaning that wherever you go, you can find one that works for you. But you need to have all this metadata, obviously, about the bands that come with it. Yeah, as you can see, it's a secant, which means that it cuts the surface of the ellipsoid. Transverse and conformal, obviously, because you can measure things on a Cartesian plane. Okay, working with maps. So how do you get this map data together? Usually it's in one or two formats. It's either the raster format, which basically means images, or the vector format, which basically means SVG. That's what we've been playing around up until now. Now the SVG, obviously, when you get it, you can get it in two forms. The SVG that you're familiar with, it lives in the page and it's projected, right? But for spatial data, you can also have it in latitude, longitude coordinates, and that is unprojected, meaning that you eventually, when you want to show it, you need to do the projection. So what software do you use? Obviously, there is quite a bit that you can use, and that spans from general visualization tools such as Degree, all the way to specialized software that is built for dealing with maps and with geospatial information, such as the shape files from ESRI. So we're going to see how to use it with D3, but also how we use maps with some sticky map layers. I'll tell you what it is in a second, such as Mapbox, Leaflet, and others. I won't do it with Google Maps, but if you're interested, I can tell you a bit about it. And you can also use other tools that are a little bit more sophisticated, that have a grammar such as the Vega and Vega Lite, because those they also support maps. Okay. So the ingestion format are mostly the same. It's usually JSON that is specific for maps, because you need to encode latitude, longitude, and you need to encode the perimeter of the objects that you want to track. And so this allows to do it. The shape files were really the first one to materialize geospatial data, but it's a proprietary format. However, a lot of data are in shapefile format, so you need to understand a little bit how to use it. Yeah, these days the GeoJSON is quite popular, so that makes things a little bit easier. Now the maps that you are familiar with Google and others, they all basically work more or less the same. They work by serving local data based on the area that you're interested in looking at. And so the way this is achieved is by having a server that is going to provide you those data and requests. And those are called time map servers. The maps that come with it are called sleepy maps because you can quickly move around it. And the sleepiness of it is created by the fact that they're mostly done with SVG. And so you don't need to download a lot of data. Now the time map server, you have quite a bit that are there. I didn't add here Google, but obviously Google has its own. And what they do is that they provide you a service where you can request by, you see here, you can put XYZ that is that long in altitude, and then you can specify what type of map you want, and they're going to send you these tiles that then you can display in your player. So here is an example of Mapbox that is in the page here. And so you see as I move around, you see that some areas they just come in, right? And this is Mapbox that is I don't know what is implemented here. We can look at it, but it's basically going back to the map server and saying, oh, now I need the tiles for this area. And so you see them, you see, coming in, right? And this is based on the Z, sorry, is the resolution for the tiles, and the XY is as you would expect the coordinates for the tiles in the plane. So we're going to see how, if I can get out of here. Okay. So everything that you saw in the map is basically vector data, right? And so this is encoded usually in this JSON format that is called GeoJSON, spatial JSON, and it looks like this. This is actually just from map of the states here in the US. And you see it's a bunch of features, each one with some properties and the geometry. So the geometry is what you expect, is the boundaries of the feature. Here it would be this particular state. And in fact, you can only specify a GeoJSON file by these three properties. The first one is the geometry, and you have choice between points, line strings, polygon, etc. Most used are probably the point for points of interest, and the polygon for having boundaries for states and countries. And then the geometry is to specify an array of coordinates. And here you see that these are in longitude, latitude. Okay. So this particular one is just an example for a point of interest that is of type point and does the long map for the coordinates. The features they have a geometry, such as the one we just discussed, are of type feature, obviously, and then you can associate also a property. So the properties, you can put whatever you like in there. So here we've added a name, that is UFC, but you can encode your data in there if you need to. And then the feature, you can also group them together in what are called feature collections. So one or more features together. So the features collection have an array of features. All right. So it's not more complicated than that, but the file might look complicated depending on what it is that you're looking at, right? In terms of resolution and in terms of of size. Now, the one problem that comes up with describing boundaries with GeoJSON is that you end up with very large file size. And the reason is that each feature, here, for instance, for the United States, for each state, I would define one feature that is the boundary of the state. And then you have all these places where two boundaries are contiguous one to another, and that are going to get duplicated, right? And so it doesn't look like it, but depending on the resolution, it may be quite a bit of data that is encoded twice, right? So our good Mike Bostock, who always has a solution, thought about encoding this topology information into the file format. And he did this with this format that is basically a GeoJSON format, but that he calls TopoJSON. That encodes the fact that you have these boundaries that are redundant. And so you just do ensure that they're only appearing once in the file, which allows you to cut by a factor of 10 almost the file size. So how this works, you can guess it. If you have a boundary, then you only encode it once, and the remaining parts and the boundary itself is what our Mike Bostock calls arcs. So you end up encoding the arcs as opposed to the shape, but you obviously need to preserve the properties and the rest of the information that we had originally in the GeoJSON. So this is more efficient, but obviously there is quite a bit of indexing. This is indexing the segments of arcs. Suddenly it's very difficult to understand anything in these files, right? On top of that, obviously, this was done for Diffie, but people are using this format now for other things, such as in Vega. Yeah, so the players that the renderers that are going to render these maps, they don't understand this format. So you eventually always go back to the GeoJSON. Once you have your TopoJSON, you move to a GeoJSON format before you give it to the software so that they can actually make sense of it. And that's what I wanted to cover here. Let me see if we have time. No, we don't have time because it's 55. Okay, so I'll finish this next week. Next week, no, hopefully this Wednesday.